All right, so now we've got our different plate tectonic zones here. And so we have this idea of things being driven by convection currents in the asthenosphere. So there is a little information about that here. If you look on this page here, you can see the convection cells in the asthenosphere right over there, right? So if they ask you where the convection currents are, there's your answer. All right, now what's the reason for these convection currents? Density changes. When things get hot, the density goes down and they rise. Okay, we also have things called hot spots, and these are located over mantle plumes. These are single spots that go up like chimney stacks in a way, and as the plate moves over it, the volcanoes form above this, and then they move over to the side and they die. So that is our notion of hot spots, and you get a lot of information about hot spots, where they are, on the reference table on our plate tectonic page. So if you're asked where a hotspot is, there's a couple that are interesting that meet up on spreading zones, like one over here and this one are pretty close over here. But most of them are kind of isolated away from different spreading zones. Okay, just fixing the camera a little bit there. All right, in a divergent boundary, what we have is that the plates are moving apart. We get new crust there. With the mid-ocean ridge, in the center of the ocean, we get a rift valley and new crust happening in the middle there. And because these things are separating apart, the youngest rock is going to be in the middle. And as we move out, the older rock, the hottest rock, is going to be in the middle. As you move away, it's going to get colder. Then we learned about magnetic striping, how the magnetite gets frozen in its orientation to the magnetic field. And the reason why I put a B over here and a B over here is these are two magnetic stripes. They're in the same direction, and they're also the same age, and that's because they were once in the center here. In the convergent boundary, we have features like volcanoes and trenches and islands, and most of the islands are going to be volcanic, and mountains. And just to give you an idea, everywhere that you have these type of things, you're going to see this pattern here, and you can tell which side is going under and which side is going over by looking at the tabs. And the tabs are always on the overriding plate, the one with the less density. You also see that we have trenches here. We have these little tiny islands along here. Those islands are volcanic islands. So those are our subduction zones or our convergence zones. And we'll find things like mountain ranges as well in places like where India is crashing into Eurasia, right? Okay, this is subduction. The reason why the ocean crust goes under is its greater density. The continental crust is less density goes up. And there's your trench right there, and we'd expect volcanoes to form where this stuff melts. It ends up going upward and creating volcanoes. So then we have our side-to-side motion of the transform boundary. The most famous one is the San Andreas Fault. You expect fault zones, earthquake-prone areas, a side-to-side motion. All right, so now I'm going to start doing some writing in here, kind of caught up with where I think I was in class. So if you have an earthquake, if things are going with earthquakes, a lot of times you're going to need to prepare for that. So you want to have food. You want to have first aid kit with you. Maybe in that first aid kit you have medicine, you have things that you're going to need, like bandages and things for people who get sick. You might want to have fresh water too, because a lot of times the earthquake might cause the water lines to be destroyed or damaged. And you really want to have some type of plan, but I wouldn't put down to make a plan before, because that's kind of common sense. Everybody should know. What are some of the things that you might want to do? For people who live in earthquake zones, you might want to have a plan already done that you've reinforced structures. And that just means that you made sure that those structures can handle things. In a volcano, you want to have an evacuation plan, all right? Because you better get the heck out of there. A tsunami is a giant wave that's going to be caused by an earthquake. That's the reason why we have tsunamis. Not because of the tides, not because of the moon. And so for tsunamis, all the things I did for the earthquake would probably be a good idea too. We might want to add a couple while we're thinking about it. A lot of times you might want to have a radio in line with things. I think flashlight is also a good thing too. Even though people are going to use their phones and stuff like that, phones are going to die out after a while if there's no electricity, so we want to have flashlight, maybe extra batteries. All right, let's go to the next thing. All right, so I know that none of my classes have started this section And so we're going to have to work through this together. So I'm hoping that I'm not going too fast, but here we go. So weathering is the breakdown of rocks. The breakdown. And physical weathering, it's going to cause a change in size and shape. But the object is, the rock is still going to be the same rock. It's just going to be smaller, rounder. And a couple things that were really important with physical weathering, one of the major things in New York State is frost action, where water seeps into cracks, it freezes, and when it freezes, it expands, and that cracks the rock open even more. The climate should be cold and wet, or humid. And we're going to find that that's going to be a lot different than chemical weathering. All right, so let's talk about chemical weathering. Chemical weathering is a change in the chemical nature. So we're really getting something new. Like we can take certain rocks and put them in the presence of oxygen, and we get oxygenation or oxidation and rusting. Sometimes caves are formed when water, which gets a little bit of acidness to it, becomes acidic, runs through, and if it has limestone, it will eat away at the limestone and form caves. Look at what's different. The climate here, instead of cold and wet, has to be warm and wet. All right, so why warm and wet? Well, if some of these things involve dissolving, and if I want to dissolve something like sugar, put it in warm water. I've got to have water to dissolve it, so I want wetness for water. I put it in warm water, it will dissolve faster. So some examples of chemical weathering really you should know about would be the fact that we have calcite reacting.
Hello again. All fourth graders, please return to your projects if you haven't already. Thank you everyone for participating in the 50-50 raffle.
Soil.
We will announce the winner at 7:45. There's still time to get involved if you'd like. The 50-50 is located at the concession stand. Speaking of concessions, thank you all so much for supporting us by buying pizza. It was very popular. We're going to have to do it again next year. At this time, fifth graders, head on out and check out the other projects. Please return to your project by 7:40. Thank you.
All right, they're having the expand here tonight. All right, so what we have here is, for definition, it's going to be a mixture of weathered bedrock and organic remains. That's what makes soil special. It has some organics in there, the remains of living things. Now sometimes, like where we are, we have transported soils. And what that means is that the soil came from somewhere else. It was transported. Glaciers brought much of the materials to our soils, to this area. And when we look at the minerals in our soils here, they don't really match the minerals in the rocks deep down below. So we know that the soil didn't come from the weathered remains of the bedrock that was below here. It's transported by glaciers. So that's usually a factor. And our soils are transported by glaciers. Residual soil means that it formed from the bedrock below, and usually it forms in different layers. So here's just an idea that we would have probably 3 important layers. The topsoil layer contains an organic mixture that's called humus. And you must remember that, I guess. That's a good way to say that, all right? So that is organic remains, along with a really super weathered bedrock. So it's very fine. When we get down in here, we have the subsoil. The thing about the subsoil is usually is mineral rich, because when water runs through the soil, what it does is it brings down the minerals. And remember, water going through the soil, that's called infiltration, right? So in the bottom here, we're going to have some bedrock that is partially weathered. And then down here, we'd have the bedrock itself, the rock layers themselves. So we really have 3 layers of soil and bedrock down below. And what we're going to find is, if this is residual soil, the minerals in here will match the minerals that we have down here. Okay, streams. Discharge is the amount of water transported by a stream, the amount of water. And after rain, you have more water, so what happens is the velocity of the stream increases. So we can make a little chart that says something like this. if we have the velocity or the speed of the stream and the discharge, which is the amount of water, as the amount of water goes up, the velocity of the stream goes up. You see that after a rainstorm, your streams are running really fast. Another thing that's going to increase the velocity of the stream, besides the discharge, is the slope. As the slope increases, velocity is going to increase too. Hey, water's going to go down a steep slope, just like a bicycle would go faster, water's going to flow faster. And as discharge increases, velocity also increases. Okay. Now, when a stream is flowing, it's going to be carrying materials. When it gets to a large body of water, its velocity decreases. And because its velocity decreases, it will start to deposit, and it will undergo what we call deposition. So, rivers that enter a body of water slow down, and there's more deposition when, okay? So we get more deposition when we have more sediment and less velocity. So what a delta is at the end of the river, so here's the river flowing here, the river tends to start to slow down and branch out like this, and because it's slowing down, it's going to drop materials, and we're going to get a almost like triangle shaped formation that we call the delta. And the most famous delta is the Mississippi Delta, and the Nile Delta. The Mississippi Delta is going to be found down around here, and the Nile Delta is found right around here. Okay, let's move on. Watershed drainage basin is the land area that a river drains. So I'm going to use a little space over here, and what will happen is if we look at an area, we're going to see a lot of streams that bond together, almost like tree branches here. And eventually they end up in one major river. So what we call this area that's being drained by this major river is we call this area right here a watershed area. So our area, our watershed is, we're part of the Hudson watershed. Our streams eventually reach into the Hudson. Let's say this is the Hudson River, and this is our side of the Hudson, and on the west side, we're going to find that we have streams, and there's streams. This whole area is being drained into one big river that flows to the ocean. So what separates one watershed to another is the fact that we have a hill here. We have something where the water has to run down on one side, and then there'd be another watershed over here. Okay? How sediments are carried. Smallest particles are carried in suspension, and that means, suspension means that they don't sink to the bottom. So the smallest ones always remain kind of floating like that. A lot of times those are called colloids. These are particles that don't sink. Some dissolve. And so if we have things like salt, that's just going to dissolve, and it kind of disappears and just flows downstream. So that's called solution when something dissolves. Okay? And the largest are going to roll along the bottom. They're going to kind of bounce along the bottom. And as they bounce along the bottom, they undergo actually a type of physical weathering. Let's go back to physical weathering and add this abrasion. So what abrasion is when you start off with a jagged rock and it starts to roll down the river, the pieces get broken off, and the rock over time becomes more rounded and smaller. So it becomes a rounder rock, a smaller rock, and also a smoother rock. So what's going to happen down here is we're going to have abrasion happening. Okay, this stuff right here, streams moving stuff along, all examples of erosion, which is the movement of sediments or rock fragments. And the driving force of erosion is actually gravity. That's a force, right? The source of the energy for erosion is actually the sun, but the force is gravity because things want to go downhill. Even the fact that we have wind causing erosion has to do with gravity too, because in a way you have air density differences moving one part up and the other moving things downward. All right, so we got wind erosion can cause sand dunes. So let's draw a picture of a sand dune. We'll talk a little bit about how I can tell which way the wind was blowing when the sand dune was formed. This side over here is called the windward side because the wind blows up this way and then comes down over here and it rolls the sand down, and then so the sand dune actually starts to move. So this is called the leeward side, and we've heard those words before when we studied climates, right? So the windward side of a sand dune has a gentle slope. Deposition is the, I'm going to use the word in here, the depositing of sediments. Okay? And the sediments are usually deposited in a sorted way if we have a stream. So let's just draw another picture that we should be familiar with over here. Here's a part of a pond, or it could be the ocean, and we have a stream flowing into that. And when the stream reaches this, what's going to happen is its velocity is going to decrease. The velocity decreases. And so the largest particles get deposited first. This is a type of sorting, and then the sorting is called horizontal sorting, and so on. So over here we might find pebbles and cobbles, P and C for pebbles and cobbles. The next thing on the list, as far as sizes of sediment, if you forget, is on this page. And this goes on how fast the stream has to go to move particles. I won't really get too much into this. When you use your Barron's book, you're going to go into this a lot more and get some explanations if you need to. But what you're going to have is you're going to have pebbles and cobbles, probably not boulders, but pebbles and cobbles. The next would be your sand, then silt, then clay, and then we go back to those things that never set, that are called colloids, that are going to form out here. So this is likely to form a sandstone over time. This is siltstone, a clay, and then we might get other types of evaporites out here. Now we could do the same thing with the idea that the rounder particles settle faster because there's less air resistance to the denser ones. So we tend to find the rounder, denser, larger particles over here, and we move away over here. Now that's one type of sorting, and that is called horizontal sorting. But every once in a while we can find a type of sorting called vertical sorting. And it usually happens after something like a landslide or a giant flooding event. And in this case, we get a big mixture of sediments all deposited at one time. They're all mixed up, and they're suddenly deposited. This mixture then sorts itself out so that the roundest and largest are at the bottom. And then as you go upward, things become less dense, more flat, and smaller. So this is what's known as vertical sorting after a flood, in which a lot of things are pushed in very quickly. This is the pattern that you get. So in a stream, where does erosion occur? And in a stream, we're likely to find places where the stream bends back and forth. These bends are called meanders. You remember being on a water slide, the water will always go to the outside as it goes down the slide. And that's because the water moves fastest on the outside. So I'm calling this the outside over here because if I bend my elbow, this is like the outside of my elbow. And so since the water's moving fastest out here, we're going to find that this area is going to have erosion. And here it is again on the outside over here, erosion. So erosion occurs on the outside bend, and deposition is going to occur on the inside bend. See, where there's more erosion, it's actually going to make things deeper. So in a stream, where does erosion occur? It occurs on the outside bend and also where the water is fastest. All right, so I'm going to zoom in on this because they really show nice pictures over here of what's going on. The depth will then change too. So if I'm looking over here, across here, I'm getting more erosion on the outside. The water velocity is going to be greatest over here where there's less friction on this area here, but there's not any water flowing at fast velocity. So here we're going to get the greatest velocity right here, not along the side exactly because there's going to be friction there, there's going to be friction there, so we pick a point in the middle. Over here, this is a straightaway, we get the fastest velocity right in the middle. Over here we have a bend, so we get the fastest velocity on the outside. So over here I'm just going to put an E for the erosion side here, And then we should also point out that there's going to be a spot where the amount of erosion is equal to the amount of deposition. And that's our equilibrium point right there. That means for every grain that's eroded, a grain is deposited, and there's really no difference. So on this side, while we have erosion, on the inside, we have deposition happening. Okay, so we go back over here to my picture over here. I'm going to put in deposition here, deposition here. Okay. All right, let's go to the next page. In a stream, where does deposition occur? Well, I think we got that. Deposition is going to be occurring on the inside of the bends, of the meanders, inside, and also where it's slower. And so in the diagram, one side is always shallow and the other side is always deep. Just going back to that, you can see that in this picture. Here's the deep side with the erosion, the shallow side has the deposition. Okay, glaciers. When glaciers come through, they take the V-shaped valleys that streams made and turn them into U-shaped valleys. And what I mean by U-shaped is that you would have this happening as the glacier moves down. And sometimes water might pour down through here and give you what are called hanging waterfalls as well along these U-shaped areas. So hanging waterfalls along the U-shaped valleys. Okay, mixed sediments. When the sediments are mixed, we say that they are unsorted. So what happens with these glaciers, I'm going to go over here to this picture, this side over here, is that as the glacier moves down, and it's moving probably to the south, it's carrying along with it stones that it's picked up. And then it reaches a point where the glacier melts right here. It actually starts to melt, and we get a lot of water coming out of that glacier, but this stuff piles up. And we call this glacial moraine. And the glacial moraine is going to be, it's going to be mixed and unsorted. So that's in front of the glacier, okay? But I do want to point out to you that in this part of the glacier, this is called the outwash plain. And in this part of the glacier, you have streams. And what streams do is they sort out the sediments. So in the outwash plain, things are going to be sorted, but in the moraine, they're going to be unsorted. Okay. Now, one type of structure we have, oh yeah, let me go back to this. Some of the rocks are going to be scratched by the glaciers, and so we are going to find that we might get scratches called striations. And if I see a rock that has scratches in it that are orientated like this, then I know that the glacier moved either this way or that way. So the glacier motion is usually along the striation. And then sometimes we get boulders that just don't match up with what is nearby, and those are called glacial erratics. These are large boulders. There's plenty of them around the Monroe Woodbury area for you to relate to. One type of structure you can get is a drumlin. Drumlin is a big hill that looks a lot like a sand dune. It's made of mixed, unsorted materials. But here's the thing. Sand dunes, we said the wind went up this way to create the sand dune. But in a drumlin, it's almost like going to the playground and going down a slide. You go up this side and you go down this way. So the glacier motion is up the steep side and down. Okay? Now, we also have around here kettle lakes, and they form when we have a glacier in which a block of ice breaks off the glacier and it creates a hole, and here's a hole right here, and then that area just fills up with sediments. Looking back at this, you can see that in front of here we're going to have a lot of material. If a piece of rock or ice broke off, right, it would be left over here, sediments would build up around it, and we get something like this. And then when the ice melts, it leaves behind a depression which fills with water and gives us a kettle lake. Okay, so landscapes. Landscapes are going to be determined by a number of things. First is climate, second is bedrock, and geological structure. So let me talk to you about climate. If you have a hot, humid climate, the features in a landscape tend to be smooth. If it is dry, like in the desert, hot and dry, they tend to be more jagged or more angular is another word we could use for that. Now the other thing about landscape regions is the bedrock itself. What is the bedrock? And what I mean by that is we have bedrock that could be made of sedimentary rock, and then typically we group metamorphic and igneous rock together. And the sedimentary rocks are going to be part of the landscapes that make up plains and plateaus, while the bedrock in mountains is usually metamorphic or igneous. That's why the Catskill Mountains aren't actually mountains, because they don't contain any metamorphic or igneous rock. And then we have the geological structures. So sometimes what will happen is you might have folding. Folding would be mountain ranges. Or you might have faulting. That's mountain ranges. So those are geological structures. All right? And so here we can see a diagram which gives us three different things here. You see how this is low level. This would be your plain. The rocks are flat. They're horizontal. Horizontal rocks that have been pushed up create a plateau. Those horizontal rocks are your sedimentary rocks. And over here we can see folding happening here. Metamorphic rock. So that's going to be our mountain. Also, the relief is a lot greater. The difference between the highest elevation and the lowest elevation is the greatest in the mountains. Over here there's very little relief, very little difference between high and low. And over here there is a medium difference. Okay, so mountains elevation is high, plateau is medium, plains is low, bedrock is going to be sedimentary, and then igneous and metamorphic. Okay, sometimes you have to match up drainage patterns with different areas. So what you need to do is you need to look at how the topography is, how the elevations are. And I'm going to leave that up to you going through the Barron's book and trying different ones and seeing what the answers are as to whether or not you can picture in 3 dimensions how you can go from one thing, which is like a side profile, to a aerial view. All right, half-life. To find out how old certain types of rocks are or certain types of fossil remains are, we use half-life. It's the time it takes for half of an unstable atom to decay into a stable atom. So if you remember, we always get a chart like this where we start off 100%, and as this goes down, the daughter product, what it turns into, goes up. Now, uranium-235, all of these are mentioned on the front page, and after that they don't really give you too much information. But what we would use this for are remains of organic things, living things, within the last 50,000 years. I wouldn't go past that, because after 50,000 years, the amount of carbon-14 becomes so small we really can't detect much of them. Potassium, this would be for your standard rocks around the dinosaur times, and what you do is you check the rocks themselves, and the fossils are about the same age as the rocks that surround them. Uranium, this is for the oldest rock fossils on Earth, oldest rocks, and that's because its half-life is about the age of the Earth, 4.6 billion. And this is for stuff in the outer space where things are really super old. Okay, so over here this would just be your standard rocks. All right, so how does half-life work? Well, what you do is you start off with the idea that if you have a half-life problem, you probably want to set up a chart that looks something like this. So I'll use carbon-14 as an example, which has a half-life of 5,700 years. I set up a half-life chart. It goes like this: half-life, and then I put my number of years here, and I put my carbon-14 over here, and carbon-14 changes into nitrogen-14. And I start with 0. And at 0, I have 100% carbon-14 and 0 years. So after one half-life has happened, this goes down to 50, this goes up to 5,700, and this goes up to 50. Because 50 and 50 gives me the original 100. And then I can put a 2 here for 2 half-lives. This would go down to 25, this would go up to 75, and this would go to 11,400 years. I usually don't ask questions for more than 3 or 4 half-lives, so I'll break this apart to 12.5 over here. This becomes 87.5, and this becomes another 5,700, becomes 17,100. Now there's nothing you can do to change the half-life of these. So if you crush the rock, you heat it, do anything to it, it will have no effect. Can it change the half-life? Absolutely no. Not going to happen. All right, rock layers. If rock layers are undisturbed, then we use what's called the law of superposition, the oldest layers on the bottom. Now occasionally what happens is we get an unconformity where the layers have piled up on top of each other and we have a gap in the fossil record, because in an unconformity we have uplift for an area, then we have weathering and erosion, and then we have subsidence, and then we have new deposition happening. And that leaves a gap in the rock record. Now we also have these rules that if we have intrusions or faults, they have to be younger than the rocks that they are in. And marine fossils on top of a mountaintop indicated that the land's been uplifted, because marine fossils were formed in the ocean, and we find a lot of places where marine fossils are found high up. It tells us that we've had some uplifting, and uplifting, folding, faulting, they're all evidence of what we call crustal activity. Sometimes we can use contact metamorphism to figure out which came first. So if a rock layer has these whiskers, or they call them ticks in here, the rock layer had to be there before, it had to be older. So this rock layer was here before this igneous intrusion, but this rock layer up here, it doesn't look like it was. And I could tell that if it was, and this was an intrusion that burnt its way through here, I'd see those marks on the top too. Okay. All right, be able to tell the difference between folding, faulting, and tilting. So a fault, let's see what we got here. A fault is when one side goes up, the other one goes down. Here's an igneous intrusion. Folding's like this. And rocks are originally deposited horizontally, so tilting is a sign that crustal motion has happened. Volcanic ash makes a great time marker. So I'm going to use that little bit of a space here to talk about volcanoes and stuff. So when we have a volcano that's erupting like crazy, it's going to send a lot of ash into the air, and that ash is going to be deposited in a wide area, large area, over a short period of time. So let's say thousands of years go by, the volcano dies out, and we get new layers of rock piled on top of it. Okay? Every time there's a volcanic ash eruption, these things have their own chemistry. It's kind of like on the forensic files where they find like chip paint on a car that's been crashed into, and they analyze the paint, and it's just got a certain chemical makeup that makes it only found on Ford cars or something, and they figure out it had to come from this guy's car, and they arrest him, right? So each one of these layers here has its own chemical signature. So if I find this anywhere in the earth, around the earth, because it's been shot all over the earth, I know it's the same age as the other layers that correspond with it. Okay, index fossils make good time markers because, first of all, they're widespread. Just like the volcanic ash, they're widespread. They have a large geographic range. The other thing is they have to be short-lived. That, unfortunately for them, their existence on Earth didn't last very long before they became extinct. And they really should be easily found. They should be the type of fossils that aren't really hard to find, so they should be fairly common. So we have a list of all the index fossils on the reference table here, and you can match them up. I'm sure when you get into the Barron's book, you're going to be doing some things with these guys over here and how they match up here with the different times. Okay? Geological history. How did the atmosphere first form? We go back to the molten earth and lots of volcanoes spewing gases all over the place as the earth cooled, and creating an atmosphere. And this atmosphere had no oxygen in it. It was poisonous, actually. So the volcano's just spewing out steam, creating the early atmosphere. How do we get the oxygen? Well, once the oceans formed, early algae took CO2 and changed it into an atmosphere with the carbon taken out, changed that into oxygen. So it was early algae. And if you need information about when that was and what happened about that early algae, you can find that information over here, where we got that oxygen into our atmosphere. Okay? Now, Precambrian time is 4 billion years long. What type of life existed? Only the simplest forms, and that means that we rarely find fossils, that fossils are really rare. That's because they were soft-bodied organisms, rarely found any fossils from that period. Now, in the time scale, when we look at the time scale on here, it doesn't look like Precambrian is really a long time, but when we did that lab with the tape, if this was the tape for the Earth's history, Precambrian was like this much of that tape. So this was Precambrian, and then the other errors we broke down in there. So Precambrian is a major time. Now, life evolved from very simple organisms, and over time they became more complex. And we really call that idea evolution, that things form from simpler to more complex. Now, we think asteroids had an impact on our planet. Asteroid impacts are thought to be the cause of mass extinctions. We talked about how the dinosaurs died about 65 million years ago because of an asteroid impact. And asteroids do leave craters behind on the Earth, but unlike the Moon, the Earth has weathering and erosion going on, so while a lot of those craters disappear, on the Moon those craters remain, and we can still see them today. So let me just remind you about that asteroid impact information. It didn't just wipe out the dinosaurs. You can see they mentioned the ammonoids, and if you look over here on these timeline here, you can see the dinosaur line stops here, and also the ammonoids. Ammonoids were animals that kind of look like these snail shells down here. Okay? All right. Weather variables, air pressure. The instrument we use is the barometer. Oh boy, B-A-R. Okay, barometer. And we use millibars or we use inches of mercury, Hg for mercury. Okay, temperature, thermometer is the device. And we have different scales. We have Fahrenheit, we have Celsius, and we have Kelvin. And all the conversions for the barometer and so on, they're on your reference table. You probably remember where they are. Okay, there we go, if we have to convert things around. Okay, dew point, relative humidity. Dew point is the temperature at which precipitation is going to occur. Temp at which So on your station model, sometimes you'll see something like this on your station model. Here, just draw this out with a couple bands on here. You see an air temperature, maybe it's 32 over here, and then it's 31 over here. This would be an indication that we're really close to the dew point temperature and rain is likely. Relative humidity is the amount of moisture in the air, and what I'll just put down for relative humidity is 100% usually equals precipitation. So the closer we are to 100%, the more likely it is to rain. Now, for the dew point and relative humidity, we're going to use a device that's called a sling psychrometer. And that's going to give us a wet bulb reading and a dry bulb reading, and the rest is up to you. We've done this chart a lot, and I think that you should be pretty good at using that. Wind direction. Winds are always named from where they came. So named for where they came, not the direction that they're blowing in. It's named for where they came. Okay? Wind speed is typically measured in knots. And what we're going to use for this is an ammeter. Oh my gosh, that's the wrong name. Let me go back up to wind direction. We use a weather vane for that. And this is called an anemometer. An ammeter is something you use to measure current. Okay. Okay, pressure. The reason we have pressure is unequal heating. High pressure. High pressure is usually cold temperature or cool temperature. Low pressure is usually warm. High is usually clear. Low is usually cloudy. Precipitation. High is usually dry and low is usually humid. Okay? So the direction of the air around the pressure systems is different. Around a high, it's outward and clockwise. And a low is inward and counterclockwise. And wind always goes from the high to the low. Okay, let's move to the next page. Winds are caused by the uneven heating of the earth and the differences in density. And basically winds are part of convection cells. So when we have an area that one part gets hot and the other part remains cool or cold, hot air rises. It does RECC, rises, expands, cools, and condenses. I'm going to bring this over here. Cool air comes down, and we get our convection cell like that. The wind blows from the high to the low. What do I mean by that? This is low pressure over here because it's lifting. Over here is high. And because it's lifting and do this, we're going to get our rain, our low and lousy, and over here, high and dry. All right, so if we go back over here about this, winds blow from the high to the low. Isobars close together will give us high wind speed. Okay. Then we have this phenomenon around beaches where during the daytime when the sun is out, okay, the land, which has a high specific heat, heats up faster and becomes warm during the daytime. And so the air over the land moves up and over the ocean moves down. And during the day we get a sea breeze, okay, because this is going to be hot. This is going to be cool over here. This has got high specific heat, I'm sorry, low specific heat. And this has high specific heat. But then at nighttime, when it's nighttime, the water, which is a poor absorber, is also a poor radiator. The water is now warm. It's heated up all day. The land is now cool, and we get the opposite.
Hello, everyone. Our evening will be wrapping up in about 10 minutes, so it's time to announce our raffle winner.
All right, I'm going to keep on going while these people are talking behind me. All right, dew point temperature. We already talked about the air temperature at which the air is saturated. Here is your dry bulb, wet bulb. When the air temperature equals the dew point temperature, we have 100% relative humidity and 100% chance of precipitation.
738.
Relative humidity is the percent. Condensation forms clouds.
Again, the
Steps
winning
for
raffle ticket
condensation.
number is 743738.
The air rises, it expands, and it cools to dew point,
We have a
and we
winner.
get condensation.
Congratulations, and again,
The
thank you
Coriolis
all so
effect
much
is
for
the
another successful
deflection of the
expand
Earth's,
year. Good night.
the deflection of things like wind and ocean currents due to the rotation of the Earth. And in northern hemisphere, things deflect to the right. Air masses refer to a bubble of air which has a certain humidity and temperature over the surface that it forms. And MT would be what we call a maritime tropic air mass. And because it's maritime tropic, maritime means it's formed out of the ocean, it's going to be humid, and it's forming from the equator, the tropics, so it's going to be warm. Continental polar. As an example, continental would be dry and polar would be cold or cool. Okay? So I'm sure in your Barron's book we're going to look at some different types of air masses there, and you'll get your information about that. A front is a boundary between the two, and what you have to remember is in a cold front, cold air forms a wedge here and creates really severe weather, like thunderstorms and possibly tornadoes. In a warm front, the warm air moves upward and the cloud is expanded, and so we get steady rain. In an occluded front, the warm air is popped up above here, and once again we get rain. Then we also have a stationary front. Now, all the weather in the U.S. moves to the northeast, and so in a map of the United States, where here's Florida, here's Gulf of Mexico, and so on, almost all the storms move in this direction. Now, that's not always true with every place, and so for different latitudes, you might find the storms moving in different ways, and the way that you can tell the direction that the storms are moving is by looking at this. See, we're in between 30 and 60, and it shows we have southwest winds, which moves our storms this way. And one of the things that move the storm are these high-level air currents called jet streams. So you might hear that refer to what moves the storms along, are these jet stream air belts. All weather moves to the northeast. Station models, we learned about conversion. Remember the 500 rule? That on a station model you can only write down 3 numbers. And so if this is my station model over here, and I'm just put this wind thing out like this, and I see the number, let's say 982. I have to do the 500 rule. And the 500 rule says that if the number is less than 500, hold on a second. I need 10 more minutes. Bye-bye. If the number is less, you put a 9 on it. And if it's greater, you put a 10 on it. So if I go the other way, if I want to convert this and put this on here, this would be 009. This one over here, if I wanted to put this on here, this is going to be 9600. And this one over here, this would be 10.0. And I'll put millibars for each one of these, like that. Okay? All right. Hurricanes, preparation for hurricanes, you pretty much put everything you did with the earthquakes on that. Tornadoes, same thing as the earthquakes. You just use your common sense on that. All right, so we are up to stars right now. Stars are going to give off electromagnetic radiation. The sun radiates solar energy, and the type of energy that it mostly radiates is visible light. So when the visible light comes into the earth, it's what we call short wave, and the earth absorbs it but re-radiates it at a longer wavelength. So it comes in as visible, but it leaves as infrared. And what we learned is that the greenhouse gases are trapping that in. What are those? CO2, water vapor, so I put vapor, and also methane. Those are some sources that trap in. Notice ozone is not in there. Ozone's only blocking out ultraviolet radiation. Okay, the earth radiates heat energy as infrared heat energy. Good absorbers of light. If you're a good absorber of light, you're probably going to be smooth, and you're going to be, oh, did I say smooth? I'm sorry, that's totally wrong. Your good absorbers of light are going to be rough, and they're going to be dark. And good reflectors are going to be smooth, and they're going to be light. Good absorbers of light are also good radiators. Like I said, a good absorber is a good radiator. Specific heat is the resistance to heating, and you can get your information on specific heat on the front page of the reference table right over there, right? Okay, good absorbers, and then we have high specific heat. Which takes longer to heat up, water or granite? The answer is water. It has a higher specific heat. Now, I didn't really talk about these things in class. I didn't really get into them, but they could be on the Regents. Conduction is the transfer of energy in solids. And I use the idea of a frying pan. If you have a frying pan, let's say this is the handle of the pan, and this is where you're going to put your food, bacon or whatever that you're cooking. You're going to put it over a fire here. What's going to happen is the molecules in here are going to vibrate because of that. This is going to heat up first, but that heat is going to be transferred by molecules to molecules. So conduction is the movement of energy through a solid. Convection we've already talked about. That's where one side goes up, the other side goes down because of density differences. And radiation is the transfer of energy through a vacuum, like how the sun's energy gets to the earth. All right, here's the type of greenhouse gases: CO2, H2O vapor, and methane. All right, let's keep going. Greenhouse gases act to trap in the infrared. Okay, we talked about the water cycle. Infiltration is when water sinks in. Infiltration occurs when the land is. Okay, so a couple things on here. We want it to be permeable. We want the land to have a flat slope to it. We want the land to have a high porosity to it, a lot of pore space. And the land has to be unsaturated. It's best if it is dried out. Runoff occurs when the land is unpermeable, is steep sloped, has a low porosity, and is saturated. What increases stream discharge? What increases it? More stuff in the streams? Well, this is weird. Infiltration could. I guess if you had more water going into the ground, you might fill up the ground with water, but it's really more rain, more runoff, more melt will give you more discharge. Now, porosity is the percent of pore space, and a lot of times they'll give you diagrams like this. Each one of these has the same amount of pore space. This just has big pores, but few of them. This has small pores, but many. Okay? Grain size increases permeability. So as the size of this becomes larger, the water goes faster through it. So the larger the size, larger, usually faster. Now I do want to point out that if I mix these up, the small beads will fill in the holes here, and I'll have less porosity, less permeability. There's also something called capillarity, the upward motion. And actually this one will have the greatest capillarity. That's the capillarity winner. All the same porosity, best permeability here, but this one pulls up the water the best. It also retains water better. As grain size increases, capillarity decreases. You can see that. All right, climate, long-term weather for location. As latitude increases, temperature decreases. As elevation increases, temperature decreases. And then we have the idea that if you're located near the coast, your climate is going to be different. You're going to have milder summers and warmer winters. We can also tell if a location is in the northern hemisphere because the summer temperature will be during July and June. And so we see these are northern. And this one over here, this one must be inland because it has a great range. This one's probably near the coast. We also learned about how mountains affect the weather. And so here's the windward side. We get what's called the orographic effect. This rises, expands, cools, and condenses. We get our rain here, and on this side we get our deserts. Okay. As the angle of insolation increases, the temperature increases. Solar noon occurs when the sun is highest in the sky. Celestial objects rise in the east and they set in the west. The zenith is a spot directly overhead, and constellations are groups that are near each other. The rotation is the spin of the earth, and that defines the day for us. Okay? The cause of night and day, I guess they give it to you twice. 360 degrees in 24 hours equals 15 degrees per hour. And the evidence is the Foucault pendulum and the Coriolis effect. Revolution is the orbit. It defines the year. 360 degrees in 365 days gives us about 1 degree per day. The evidence we have for the revolution is the seasons, which is really caused by the tilt of the earth. Whoops, let me move that. And different constellations. All right, this chart is a chart that you've got to get down. The direct rays of the sun over here during this days are over the equator for the equinoxes. And then December 21st, it's at 23.5 degrees south and then 23.5 degrees north. This is Capricorn, and this is Cancer. Okay. Altitude of the noon sun, 48, hour longitude is 42. It kind of adds up to 90 if you notice that. Okay, duration of insolation, 12 hours for the equinoxes. Winter, 9, summer, 15. Temperature, mild, winter, cold, and hot. Okay. Is the sun ever 90 degrees over in New York State? No. It's only between 23.5 degrees south and 23.5 degrees north. Okay? If the Earth was tilted, would there be seasons? No. In fact, if the Earth was more tilted, the seasons would be even more exaggerated. Geocentric model, Earth-centered. The planets were moving around, but they were moving around because the Earth was spinning. Heliocentric is the sun-centered model. Okay, if a satellite is close to a star, orbital velocity is fast. The closer you are, and the more massive the star is, mass and distance affect gravity. Eccentricity is how uncircular it is, and we just did a whole bunch of stuff, so I'm going to leave that alone. Moon, one revolution for the moon, one time around, 27.3, full moon to full moon or new moon, 29.5. And you should memorize your moon chart. Here's the information about solar eclipses that we took a look at. Study them, lunar eclipses, the tides. We talked about spring tides versus neap tides. Let's look at solar system. First 4 planets are rocky. The others are gaseous. Okay, we learned about asteroids, meteorites, comets, the sun. Please read through this, the age of our solar system. Galaxies about 10 billion years old. And we'll go to the last pages here. Okay, our galaxy, like it says here, is 10 billion years old. Levels of organization. Start off with the youngest, for smallest, youngest. Let me go to the oldest. The oldest is the universe. The universe itself is the oldest. Then from the universe formed galaxies. The galaxies were made up of stars, so you needed stars before that. Okay? Of course, then we also have, from that, solar systems. And then from there we have planets and moons. All right, so I want to squeeze those in there too. The Big Bang theory is that the theory that the universe started. And what is proof of the Big Bang? We talked about the red shift, that all the galaxies appear to be shifted to red, and also that telescope discovered by accident the background cosmic radiation. Age of the universe, 10 to 15 billion years old, and the light years, the distance from the sun. Now there's one thing that I didn't really cover very much, and that is learning about stars. So I put together some worksheets for you to do on stars. Thank you very much. Have a good summer. Good luck on your Regents exams. Had a great time teaching you. Keep in touch. Bye-bye.